let us start with first experiment, that is thermal conductivity of metal rod. Aim to determine the thermal conductivity of the given metal rod. These are the specifications. Okay. So in our experiment we have aluminum rod which has a diameter of 50 mm and which has length of 160 mm. To measure the surface temperature of aluminum rod and water inlet and outlet temperature, we are using K-type thermocouples. The maximum voltage we can set in our experimental setup is 150 volt. Okay, so now thermal conductivity of the metal rod can be determined using Fourier's law of conduction. What is Fourier's law of conduction? You can see here, where Q represents heat transfer. That heat transfer is directly proportional to cross-sectional area which is perpendicular to the direction of heat flow and its temperature gradient. Where Q represents heat transfer, K represents thermal conductivity, A represents cross-sectional area, dt by dx represents temperature gradient. This thermal conductivity is related to conduction heat transfer. What is conduction heat transfer? You can see here. Conduction heat transfer is a mode of heat transfer where the heat transfer takes place from high temperature region to the low temperature region, where the molecules or atoms are at under rest. They will not move, but they may vibrate, but they will not alter their position. If the heat transfer takes place in such cases, that type of heat transfer we will call it as a conduction heat transfer. Okay, now this is our experimental setup. First I will name the parts of the experimental setup. First one is the rotameter, second one is the temperature indicator, third one is the knob which is used to vary the voltage and current, fourth one is the power switch, fifth one is the electrical heater, sixth one is the thermal insulation, seventh one is the water jacket, eighth one is the thermocouple. This is the heart of the experimental setup. Here there is an aluminum rod. That one end of the aluminum rod is connected to electrical heater and another end is connected to water jacket. For better understanding, I have drawn the schematic view here. You can see, as I told you, there is an aluminum rod. One end of the aluminum rod is connected to electrical heater and another end is connected to water jacket. Okay, where we have placed 4 thermocouples on the surface of the aluminum rod and 2 thermocouples placed on the surface of the water jacket. Whereas T1, T2, T3, T4 represents aluminum surface temperature, whereas T5 represents water inlet temperature and T6 represents water outlet temperature. Okay, then how to conduct the experiment? You have to switch on the power button. Okay, then you have to switch on the console button, then you have to switch on the heater, then you have to set the heat input by varying the knob, voltage and current. Later you have to set the rotameter reading as you want. You can set 1 LPM, 2 LPM, or as you want you can set the rotameter. Then leave the experiment for at least 20 to 30 minutes. After that, what will happens? The aluminum rod will be gets heated and it will attain the steady state. After 30 minutes you have to take the 6 temperatures, 4 from aluminum surface, 2 from water jacket. Okay, now I will explain you how to take the readings. Okay, so now this is the experimental complete view of experimental setup. Okay, now I will explain you how to take the readings from the experimental setup. So first, as I told you, so this is the first reading. As I told you, set the LPM constant, that is 0.9 you already set it, and convert that 0.9 into kg per second. Okay, now you have converted. Now first reading, I will go with first reading, that is T1. Is it right? T1 is represents what? Temperature at location 1 on the aluminum surface. Then how to take the T1? You can see here now. You rotate this T1, you will get the temperature reading here. That temperature reading is nothing but what? T1. So similarly, you take the T2. T2 is nothing but what? Temperature at location 2. Again on the aluminum surface. Then you rotate the knob and take the temperature reading here now. Now you will get the T2. Like that you have to take the readings from T1 to T6. Then those represents what? Temperature readings of aluminum surface as well as water inlet and outlet temperature. Like that 4 thermocouples and 5 thermocouples. T5 represents water inlet temperature, T6 represents water outlet temperature. After getting these readings, you have to do the calculation. What is the calculation part? You can see the first parameter is cross-sectional area. How to calculate the cross-sectional area? As we know, that is A is equal to 5 by 4 into D square, where D is nothing but what? Diameter of the metal rod. That is 50 mm they have given, converted into meter. Then substitute, you will get cross-sectional area is equal to 0.01963 meter square. First parameter is over. Second parameter, you have to calculate the mass flow rate of the cooling water. The mass flow rate, we are using rotameter to measure the mass flow rate, right? That rotameter will give the readings in LPM. So generally we are putting mass flow rate in kg per second. Then how to convert that LPM to kg per second? Then generally 1 liter of water is equal to 1 kg of water. Is it right? So then that is converted. Where here rotameter reading, what you have set it? You have set it for 0.9 LPM. That 0.9 liter is equal to 0.9 kg. Then divided to per minute is there. Convert that minute into second. Then 0.9 divided by 60, you will get 0.015 kg per second as a mass flow rate. Okay, this is over. Now you have to calculate the heat transfer rate. You can see here, the aluminum rod is already gets heated here. When you are supplying cold water inside here, that cold water is going to interact with the aluminum rod. When it is going to interact with the aluminum rod, the heat is transferred from this aluminum rod to the water. Then water becomes hot. Then hot water will come out here now. That means what? It is carrying some amount of heat. Then that amount of heat carried can be calculated with the help of an equation. The amount of heat carried by water can be calculated with the help of this equation. That is QW is equal to MW CPW into T6 minus T5. Okay. Now where MW is mass flow rate, already you have calculated, fine. CPW is the constant, that is specific heat of water, that is 4.187 kilojoules kg per Kelvin. Kilojoules kg Kelvin, that you constant. Okay. Now T6 and T5 already you have taken here, already you have taken from the temperature indicator. Then substitute here, you will get the heat carried by the water. Okay, now I got heat carried by water is equal to 106.59 watt. Substitute here. Okay, this is over. Next, how to do? Our aim is to calculate the thermal conductivity, right? Rearrange the Fourier's equation. Write it as thermal conductivity is equal to Q divided by A into dt by dx. Here, to calculate the thermal conductivity, QW already we have calculated. That's fine. A already we have calculated, that's also fine. The only unknown is dt by dx. That dt by dx we can get it from the slope actually. Okay, by graph I can get the values dt by dx. Then how to draw the graph? You can see here now. Vertical component you take temperature, horizontal component you can take distance. Okay, so now here you can see here now, this is 0 distance because heat is flowing in this direction. This is 0 and it is a 1. At T1, this is at x1 you can call. At x1, what is the T1? T1 is equal to, I will take I will do one specimen calculation. I will consider highest temperature here now. Then I will take a 6 reading. At x1, what is the T1? T1 is equal to 93.3. At x2, that is T2. T2 is equal to 81.5. T3 is equal to, like that you have to take the, you have to draw the graph here now. Same thing, x-axis at x1 0 here, right? At x1 40 mm, at 40 mm, what is the T1? 93. Okay, draw it here. At x2 temperature is 81.5. Draw it here, then mark it here. Then at point 3, what is the T3? That is 69.4. Mark here. And at point 4 temperature is 58. Then mark it here and draw a straight line. Okay, now take any two points and draw one vertical line and horizontal line. You will get the slope here now. This represents change in temperature. Vertical component you can take it here, change in temperature, and you can say here horizontal you can see change in distance. Okay, just to measure from the graph you will get values that and here also you can measure and you will get the change in temperature. Change in temperature I got as a 5 degrees Celsius. Change in distance I got it in 20 mm, but I converted the 20 mm into meter. Then I got the final answer as 250 degrees Celsius per meter. Then substitute this dt by dx here. Then you will get the thermal conductivity of aluminum rod as 217.198 watt per meter degree Celsius. It is the final result. You have to write the final result as 217.198 watt per meter Kelvin. This is how to conduct the experiment, how to conduct the thermal conductivity of a metal rod. Okay, thank you very much.